Okay, so hello everybody. I'm giving my talk from my home because some anarchists blew up some transmission lines in Berlin, and now we have no internet connection at the institute. Crazy enough. And yeah, I'm sorry for not being in Los Angeles, but I will be there the day after tomorrow. Tomorrow will be my flight. So I'm talking about thermodynamically consistent finite volume methods for generalized Nernst-Planck-Poisson problems, which basically is about how to discretize things, equations yesterday introduced by Manuel Landsdorfer in a hopefully proper way. So let us start. So, what do I understand under generalized Nernst-Planck-Poisson problems? So we assume a transport of n charged species, which are described by molar concentrations Ci and charge numbers Zi in a self-consistent electric field. And they are dissolved in a solvent with concentration C0. And charged particles move to three different forces. First, of course, do their own gradient of the chemical potential, which we assume as some kind, let's say, of the chemical potential of the ideal gas, where we have some reference chemical potential mu naught, and the low of I over a constant value of C naught. Second force is the gradient of the electrostatic potential because particles are charged, and we introduce a third force, the gradient of a so-called excess chemical potential, which is some additional force, which can for instance come from steric effects. Yeah? So this describes us basically the species of the flux. Then we have a continuity equation, which is fairly standard, where we can have some bidirection terms. And here we have the Poisson equation, which I have a little bit simplified. This is the epsilon Faraday constant. And then we have the charge density Q, which is here on the right-hand side. It's made up of the concentration. Okay, so, and we can have various alternative formulations of Nernst-Planck fluxes. Yeah, we can basically reformulate this in what I would call drift diffusion form, where we have basically some Fickin diffusion, described just by the concentration gradient, and those forces are due to the gradient of the chemical potential, and the excess chemical potential are part of a drift term. Yeah? So if excess chemical potential would be zero, then we would have the well-known drift diffusion equation, which is also very similar in the semiconductor device modeling. And third form, which I would call this the activity coefficient form, which is one can find quite a bit in electrochemical literature. Here we have write the gradient of an activity coefficient, which kind of modifies the concentration, and we take the logarithm of this, and this is basically the way particles move. Yeah? And the activity coefficient is essentially the exponential of the excess chemical potential, and without steric effect, and with basically what corresponds to infinitely small ions, then we have that the excess chemical potential is zero, and activity coefficient is 1. So, and then there are well-known ansatz to introduce steric effects, first with equally sized ions. This, by the way, goes a little bit in parallel to part of Manuel's yesterday talk, but in a slightly different fashion. So we introduce the molar volume of the solvent in the ions, which should be the same. So for instance, this could be some third power of some lattice constant A. And we introduce the incompressibility condition, which says that the summary concentration C bar is equal to our constant C naught, which we had when we introduced the chemical potential, which is equal to 1 over the molar volume, and which we assume to be constant. Yeah? This immediately basically limits the concentrations to be between 0 and this C bar. And we assume that we still use these ideal gas chemical potentials for all the particles, but also including of the solvent. And we introduce the excess chemical potential as the negative chemical potential of the solvent. Yeah? And we can calculate the concentration of the solvent through this incompressibility condition from the concentrations of the dissolved species. And this gives us basically an electrochemical potential and a excess chemical potential, which depends and couples all the concentrations. And if you calculate the activity coefficient, it's 1 over this molar volume times the solvent concentration, which we just can calculate by this condition. Yeah? So, yeah. And this basically is just describes an ansatz which is quite well known as modified Poisson-Boltzmann equation. If we talk about the thermodynamic equilibrium, I will come to this later. And basically, this ansatz ignores that we have solvation, that we have possibly varying molar volumes, molar masses. And if we introduce them, then we have basically some non-constant summary concentration. Yeah? The sum of all concentrations just somehow depends on the composition. And we also assume that each species has basically surrounded by Ki solvent molecules. And we have an incompressibility condition which just contains this, uses the solvated molar volume. And which then allows to calculate once again the solvent concentration from the concentration of dissolved species, but in a slightly different way. Yeah, and then we introduce what we also had the model which has been developed by Dreyer, Gurke, Müller, Landsdorfer, where we basically take also into account the different molar masses as a prefactor of the gradient of the solvent chemical potential here. And we also have to introduce the pressure into the chemical potentials of the species, including the solvent species. Here we have basically the molar fractions under the logarithm. It's kind of a little bit, so we don't have the constant reference concentration here anymore. And then we kind of define the excess chemical potential as the difference between the this combined chemical potential of species and minus the chemical potential of the solvent, minus this ideal gas chemical potential, and we come to this expression and the corresponding expression of the activity coefficient, yeah? Which now depends on all the species and on pressure. Yeah? So, yeah, we also could have some conditions sometimes when we would like to couple this to Navier-Stokes equation, where we assume constant pressure. We could see if the ratio of the solvated molar volumes corresponds to the is the same as the ratio between the solvated molar volume of the species over the molar volume of the solvent is equal to this expression, basically giving the ratio of, let's say, solvated molar masses. Then the density stays constant and things collapse, and then we get once again activity coefficients depending on all the species, but not dependent on the pressure. Yeah? But that's kind of side discussion, which can be sometimes useful. So, how to calculate the pressure? So, basically, this model introduces the pressure basically as so pressure needs to be calculated by the Navier-Stokes equation, and assuming mechanical equilibrium results in the momentum balance between the gradient of the pressure and the column force, which we also had seen yesterday on the slides of Manuel Landsdorfer. And there are different ways to calculate the pressure. One way would be to assume, which is, for instance, true in the one-dimensional case, and which is an additional assumption along mechanical equilibrium in higher dimensional cases. We can take the divergence of this equation and get a second-order elliptic equation for the pressure, which we then can implement with the standard finite element or the finite volume methods. So, and yeah, so let's have a first look at the thermodynamic equilibrium, which is characterized by zero fluxes, and in order to which we integrate, and we need integration constants, which we basically find from some bulk reference potential, reference pressure, and concentrations, and also activity coefficient. We can integrate the Nernst-Planck flux, introduce these constants, and we get an expression of the concentrations in this way, which we can express via the activities and the activity coefficients. Yeah. This is an algebraic system in just coupling all the concentrations, which then, of course, is once again then combined with the Poisson equation, where then now the concentrations coming from these algebraic systems are introduced, and we in addition have this I call it pressure Poisson. We have to solve this pressure Poisson equation. Yeah. So yeah, and if we go to this activity coefficients where all species have the same molar volume, we can in fact express also the activity coefficients in the activities, and this helps us to basically replace concentrations in the which just enter the description of the mass density of the charge density. We can express them via the activities, and then we just result in this well-known modified or generalized Poisson-Boltzmann model. We have the this kind of sum of the exponentials of just the electrostatic potentials plus one in the denominator. Yeah. And so this is the well-known Bickermann model, and there are many. I think it has been reinvented several times from my knowledge of the literature. And if the activity coefficients are one, we just are at the very just straightforward Poisson-Boltzmann or Chapman model. Yeah. So, and just to see what comes out of this, Poisson-Boltzmann or with the pure Chapman ansatz would look like this, where we have this kind of experimentally not verifiable parabolic behavior of the double layer capacitance curves. Yeah, so this is double layer capacitance versus applied electrostatic potential. This ideal mixture case or Bickermann case basically still overestimates this, and here if we just introduce solvation just based on this model of Dreyer, Gulke, Müller, Landsdorfer, then we get the double layer capacitances down to realistic values, and we also can just have different sizes of these camel shape humps depending on different solvation numbers, molar volumes. Yeah. So this is one case. Which basically recapitulates the discussion which had been given by Manuel Landsdorfer yesterday in a slightly different language. And just another question is what does happen with when we want to introduce. So this is basically works on the computational domain, assumes just boundary conditions at the right end of the domain where we fix electrostatic potential and pressure as bulk values, and where we have boundary conditions free of exactly. So just applied potential, of course, at the that's of course a bug in the slide. Applied potential just at the electrode, and we have this kind of natural boundary condition for the pressure equation. Yeah. So if we introduce reaction rates at the electrode interface, yeah, we assume that the solvent and metal are inert with respect to reactions. In the simplest case, only ions and electrons can react, and we assume that electron concentrations in the metal are constant. We assume an applied potential difference, and this gives us this type of theoretical boundary conditions at the electrode. We have these pressure boundary conditions, and we just have some bulk values which need to be applied at the right hand side. And then we postulate that the reaction rates depend solely on chemical potentials at the surface. And then we can assume, if you would assume fast adsorption, then we would see equal bulk on surface potentials, chemical potentials. So that means that these surface chemical potentials are said equal to the traces of the chemical potentials given in the just of the unknowns in the domain. And here, basically, this is some idea which has been introduced by Dreyer, Gulke, and Miller, which assumes that we can use the method of matched asymptotic expansions in order to have subdivided domain in some inner domain and some outer domain, and where we regard formal asymptotic expansions with the small parameter, which is basically the bi-length over the domain width. And the inner coordinate is just scaled by 1 over the bi-length. And just we assume formal asymptotic expansions just for the outer domain and for the inner domain, and match them and glue them together by just saying that so at the kind of interface between inner and outer domain, the values should be the same. So, and then what comes out of this is that if you assume that we have a large domain, we have a very small boundary polarization boundary layer, and we can basically neglect its size. So we have described the outer problem, and once again in our basic simulation domain 0L. And there comes out that we can replace the Poisson equation by the electroneutrality constraint. Yeah, so that basically the charge density is 0, and we can keep the just Nernst-Planck flux as just the model in the outer domain. Yeah, and we also keep these boundary conditions which we introduced at the electrode, and then we need to know how we can calculate the chemical potentials at the surface, which describe the reaction rates in this case. And this brings into the discussion then the inner equation. This ansatz results in just the constant electrochemical potential as a local equilibrium in the polarization boundary layer. And just from the matching, we can then express the chemical potentials at the surface as the chemical potential of our the problem in the outer domain plus the difference of the applied potential and the electrostatic potential just of the outer equation. Yeah? So, and this will give us some Butler-Former-like potential difference as bound for describing the boundary conditions. So, and then we can describe the surface reaction equations by just introducing different reacting species. Just we introduce the species number -1, which then describes the concentration of the electrons on the metal side, and then we can write reaction equations just by introducing standard mass action laws with corresponding constants. We have mass and charge conservation, which then constrains the coefficients in these reactions. And we get just assuming that electrons on the metal side, then we can also introduce the number of electrons in one direction, which is basically this Sk -1. Yeah. And from this we can define the affinity of the expression and define rate expressions, which then allows us basically to describe reaction rates just using this, let's say, expressions in the species chemical potentials, some delta G, which basically includes the chemical potential of the electrons as a constant. And here we have the number of electrons reacting plus the constant times the applied potential difference. And we can write this, So, and we can basically, so this would be the boundary conditions for the electroneutral, the Nernst-Planck electroneutral system. And we could also use the same ansatz for the rate expressions for the Poisson-Nernst-Planck system. Yeah? So that means we would be able to compare also these rate expressions, how they work for the electroneutral case and how they work for the Nernst-Planck case, for the Poisson-Nernst-Planck case. Yeah? So, for instance, for a redox reaction, simple redox reactions with n electrons reacting, and where we also introduce some inert background electrolyte, we can introduce these kind of redox reactions, and we can have affinity terms either for the Poisson-Nernst-Planck, which basically then justify corresponds to the delta G plus the difference between redox and oxidizing species chemical potentials, or for the electroneutral Nernst-Planck equation we just in addition just introduce this difference between the potential in the domain and the applied potential. Yeah. So, and then we can do the calculations, and this results in some, let's say, Butler-Former-like equation. Yeah. If we can shoehorn this into this, where we have just as the prefactor, the summary concentration over the square root of the product of the concentrations of O and R. And this kind of expression, which involves the exponential of the applied potential difference. And we can apply this as a nonlinear boundary conditions to either the Poisson-Nernst-Planck, in this case to the electroneutral Nernst-Planck system, and compare the results also with the Poisson-Nernst-Planck case. And then we see that this is just one case where ZR is -1, N is 1, and ZO is then 0. And we see the red curves are just is Poisson-Nernst-Planck, and the green curves is the electroneutral Nernst-Planck. So yeah, so which then shows behavior which we also know from Butler-Formel equations. And if we look for these really large potential differences and zoom out, then we just the mass transport limitations. Yeah, and we see a very good match for small applied potentials between this electroneutral case and this Nernst-Planck-Poisson case. But what we also see basically something which I think is something like a Levitch exclusion, where we have electrostatic effects which prevent charged species from coming close to the electrode. Yeah? So that means the rates from the Poisson-Nernst-Planck equations basically collapse here. Yeah? So this is something which one that can be discussed and would be also maybe introduce could be interesting to be discussed further during this long program. One thing which might be interesting is the question, okay, so what is about this assumption that direction really happens at the interface? One could say, okay, so let's try to introduce tunneling, where we assume that basically electrons are available not only at the interface, but also just with exponential decay within the domain. And where we just basically introduce the same reaction rate expressions as we had as bulk reactions with some space-dependent prefactor, which just contains just describes some exponential decay. Yeah? And then we can just see Poisson-Nernst-Planck plus tunneling, which a little bit mitigates these Levitch exclusion effects. And this is also something which might be interesting to be further discussed. So, but this is some kind, let's say, of investigation I'm doing, which might be interesting. So now let's see. I promised to talk about finite volume methods and how to discretize things. Yeah? So these calculations basically are based on some finite volume code which I'm having. Okay, so there are various variants of finite volume discretization methods. So the basic idea of the finite volume method is to subdivide the computational domain basically into control volumes, which kind of play the role of representative elementary volumes, which we usually also use in order to derive this kind of conservation laws. Yeah. And if we have a finite number of representative elementary volumes, we just can use the Gauss theorem to derive mass, to derive just balance laws for the representative elementary volumes from our partial differential equations. And then we need to think about how to really create these representative elementary volumes and their different approaches to this. One approach is to just take a triangulation of the domain and use the triangles as the representative elementary volumes, but just basically inspired from successful exposures in semiconductor device simulations. I'm working with so-called Voronoi cells, which you also define based on the Delaunay triangulation of the domain, which has some certain angle conditions in 2D. Also some more general conditions in 3D. So where we can basically take the circumcenters of triangles, join them, and then we see these green domains. These are the so-called Voronoi cells, which we then take as our control volumes. And so on this construction can be done in 1D, in 2D, and in 3D. And the, let's say, nice geometrical property of these Voronoi cells is that if you take an edge of a triangle and the interface between two neighboring Voronoi cells, then there's just by this construction using these circumcenters, we have a right angle between them. Yeah? So that means we can look at a concentration in given collocation points, which are then correspond to the nodes of the triangulation, and describe the normal flux between these neighboring cells just by finite differences, standard finite differences between data in these cells. So this is kind of admissible finite volume subdivision and makes it quite convenient to define proper upwinding and so on. Yeah? So if you look as an example at the discrete Poisson equation, then here we can, so just this is our Poisson equation, just minus divergence epsilon gradient phi minus q is equal to 0. Then we can just integrate this over a control volume. Then we can take Gauss theorem and cast the integral of the divergence flux to an integral of the normal flux through the surface of this control volume. Yeah, and we keep just the integral over the charge density. And then basically by introducing quadrature rules, we can just describe the surface integral as the sum of the integral of just normal fluxes between the neighboring control volumes multiplied by the size of these interfaces. And here just we have E and KL, that's the electric field, just the discrete projection of the electric field, which we can basically then express just by a simple finite difference ansatz. Yeah? So, and for the integral over the charge density, we just take just a point quadrature where we just express the charge density by the concentrations in this collocation point xk and xl. And then this gives us just the discrete system of equations. Yeah? So it can be proven that this is convergent discretization. The system matrix, so it's just in a linear system in phi, the system matrix in this case is positive definite. And we can, so, okay. So then so this is basically also just serves as an example how this kind of finite volume method is defined. And then we, of course, need to discretize the Nernst-Planck equation. And for this, we look at our Nernst-Planck flux in a drift diffusion form. And this immediately gives the idea to look at drift diffusion equations in semiconductor device modeling, where we have this Schaffer-Gummel discretization, which exponential upwinding ansatz, which is quite successful over there, which can be also derived by some basically solving the drift diffusion equation along this edge between two neighboring collocation points. Yeah, so, and basically in order to fit to this generalized Nernst-Planck flux, we then also just need to introduce the gradient of the excess chemical potential along with the gradient of the electrostatic potential. Yeah? So without the red data, it's just classical Schaffer-Gummel conductor devices. With the excess chemical potential, we just use the same approach to define the discretization for our generalized Nernst-Planck-Poisson system. Yeah? So in addition, we subdivide the time domain, and we use an implicit Euler ansatz for its unconditional stability. And we introduce these terms delta phi nkl as just the finite differences between the electrostatic potentials in these collocation points. And we just introduce a similar expression for the chemical excess potentials. And then we describe the discrete Nernst-Planck fluxes as these finite differences of the Bernoulli functions in these delta terms multiplied by the corresponding concentration values over the just length of this edge between xk and xl. Yeah. So the Bernoulli function, this is it's defined as x over e to the power of x minus 1. And it comes very, as I said, it comes really without the excess chemical potential. This comes in a very natural, just from equation on solution of the kind of flux problem along this edge between these two collocation points. So, and in a way, intuitively, this generalization by introducing the additional gradient of the excess chemical potential intuitively is straightforward, and it has been also kind of introduced several times. Yeah, at least. So we had some discussions at the institute where we thought maybe it could work, but then we found that there was some semiconductor device simulator in the 80s, which also already used the same approach in order to find a good way to discretize degenerate semiconductors. And there's a paper for Liu and Eisenberg, which uses this in electrolyte models for ion channels. So this is in a way kind of yeah, let's say intuitive generalization. You have to notice that in our ansatz for chemical potentials, the excess chemical potentials, this basically, depending on which expressions we choose, in the most general case, this really couples all the concentrations in a nonlinear way. Also, then, of course, it also depends on the pressure, and we have a kind of highly nonlinear coupling of these things. Yeah? So, this Benoit Goudel, who is now in Paris, I basically was able to just look at the qualitative properties and convergence properties of this excess chemical potential scheme in the pressure-independent case. Yeah, so which then kind of would assume that we have something like the condition for constant density. And there we can prove exact local and global charge conservation. We can also prove consistency to thermodynamic equilibrium. This means that we have basically, if you look at the equilibrium, we could have two possibilities to solve this equilibrium problem. We can use the generalized Poisson-Boltzmann problem, which basically would involve just some more generalized some discretization of the Poisson equation and then some algebraic system for the concentrations. And alternatively, we could solve the same problem using the discretized Nernst-Planck-Poisson system with boundary conditions which correspond to the equilibrium case. Yeah? Yeah? And we can prove that's what I understand as, let's say, consistency to thermodynamic equilibrium, that these two possible solutions are the same. Yeah? So just we have this kind of equilibrium problem on the continuous level, where we just express or can just integrate the Nernst-Planck fluxes and derive the generalized Poisson equation on the continuous level, and the very same procedure works on the discrete level. Yeah? So then we can also prove that the concentrations stay within the limits from natural constraints. There's a discrete counterpart of the free energy, where we also could prove that we have a decay of the relative free energy along the solution trajectories if we have the look at the approach to the equilibrium. There's a result on the existence of solutions of the discretized systems, and we could also prove the weak convergence of the discrete solutions to continuous solution. Yeah. So, yeah, and here some results, what we can see from this. So this basically are xt plots. So x is on the x-axis, and the logarithm of the time is on the y-axis. And we have here the electrostatic potential. So we just apply, just have constant concentrations, positive and negative ion concentrations, and in a binary electrolyte, and the corresponding solvent concentration, which basically comes out of the incompressibility conditions. And then we apply potential difference. And here we see basically the evolution of the electrostatic potential from just being linear to just being constant, or on the electric field of being constant to being just concentrated in the boundary layers. And here we see then the evolution, the evolving for the ion concentrations, the corresponding boundary layers, concentration boundary layers at the positive and negative side. And just, yeah, and positive ions are, of course, repelled at the positive electrode, and the negative ions are repelled at the negative electrode. Yeah? So, and we can see also then in the numerical calculations that just for this numerical example, just concentrations stay within the limits given by the conditions. And then here we see the evolution of the free energy, relative free energy. So it decays to the equilibrium value, also in an exponential fashion. And an interesting thing which we could use also numerically is to take the dissipation rate per time step size as a criterion for controlling the time step discretization step size. So here we have a two-dimensional example. These are now XY plots. And this and where we at the right side here we have just subdomains of the surface, which are differently charged. And we apply just some electric field in the y direction. And this gives rise to, depending to the possibility of the motion of the ions. So here we see the electric field applied. And then basically just these different opposite charges at these parts of the interface play a similar role as a doping in a diode. And here we have, that means we have an electrolytic diode, and we can see that with forward bias we have rather relatively high ion concentrations and the possibility to have an ionic current, and we have a lower ion concentrations and correspondingly lower ionic current if we apply the reverse bias. Yeah, and then we can see some, in this case, slight rectification effect for this current, also depending on the model which we apply. With Chapman model, or even just this model where we just use the size limitations. And we can also see that we have a second order convergence, the calculated AV curve, yeah, for this kind of accessible chemical potential scheme. So this works in a way quite well. Okay. Yeah. So now the question is, as I introduced this finite volume discretization approach, I want to say something about the way how to implement this. So basically, the problems which we are looking at can be just described as a system of n-coupled partial differential equations, which contain flux terms which depend on the solution and the gradient of the solution, which contains some possible reaction rate terms, expressions, and which contains some storage terms, which are just the terms under the time derivative. Yeah? And yeah, so charge transport in semiconductors, ion transport in electrolytes, multi-phase flow and porous media, and quite a bit more of problems just fit into this scheme. And using this finite volume discretization approach, we can basically derive some kind of nice way programming interface, how to describe the problems in this discretization of this problem class. So where we have, once again, our storage and direction terms, and where we just use discrete edge fluxes, which basically are just some possibly nonlinear functions which depend on the unknown values in just two neighboring control volumes. Yeah? So we have just, instead of SR and G, SR and G. And this allows to just, let's say, have at one side, let's say, the geometry things come from the mesh generation, form factors describing the size of interfaces, and these things at one side. And at the other side, at the other hand, we have basically the physics part, which is just described by these, in the simplest case, three functions. Yeah? So. And yeah, for solving these discretized systems, yeah, so you have the implicit Euler time discretization. That means we need to be able to solve in each time step, or if you solve a stationary system, solve the stationary nonlinear system. And here the method of choice is Newton's method with analytical Jacobian, because then we get quadratic convergence, which makes things quite robust. And then we have to solve the linear systems of equations, where we can use various direct and iterative linear solvers. And this has been implemented. Yeah, I'm working on this type of methods for quite some time, and let's say several generations of solvers. And the most recent generation of solvers in this context basically came up has been now developed in the Julia programming language. So Julia got its version 1.0 in 2018, and is a, let's say, rather new, not anymore very new language for scientific computing and data science. And it basically is characterized by just ahead of time compilation, and that means you just write code which is on a syntax level as Python or MATLAB, but basically you have the chance that this is compiled in such a way that you have a C-like performance. Yeah? It has a very good package manager, which makes it in a way easy to support reproducibility of the software. It's open source. And what triggered me personally to really give this a big shot is the easy access to automatic differentiation. Yeah? Because as we discussed, if you look at these nonlinear fluxes, they're highly nonlinear. If you want to work with this Newton's method with analytic Jacobians, we would have to write complicated code writing for expressing all the derivatives with respect to all the concentrations and so on, which makes it quite hard to implement things. Not using Newton's method also would mean taking chances because of these high nonlinearities, like fixed point iterations and so on, probably also would create quite a bit of headaches. And so basically, the idea then is to, okay, let's just help use automatic differentiation in order to create these analytic Jacobian matrices, which comes out of these rather complicated discretization schemes. Yeah? And this is basically the idea behind this Voronoi FEM.jl Julia package, which is open source, available through the Julia package manager. And uses automatic differentiation, and it works in 1, 2, and 3D. So just in the simple case, let's say in the case of the ideal mixture, this flux function for this code would look like this. We just write the expressions which describes the formulas for just calculating the residual of the problem based on flux functions between two neighboring control volumes. And automatic differentiation allows to just calculate the partial derivatives, it's all the unknowns for this kind of flux functions, and then just combined with the global sparse matrix, which then is the corresponds to the Jacobi matrix of the system. Yeah? So the automatic differentiation approach uses forward mode automatic differentiation, which is quite fast and is also just by efficiently compiled by this just-in-time compilation approach of the Julian language. Yeah. So, and this is part of now a larger package system which we are developing together with several colleagues at the Weierstraß-Institut. We have several packages on pre-post-processing, machine learning visualization. There's Voronoi VM, and Christian Merdon is developing a finite element solver, extendable FEM, which also implements very modern pressure robust finite element methods for solving Navier-Stokes equation and others. We have a package on semiconductors, perovskites, on top of this Voronoi FM code, and I'm developing a package called liquid electrolytes, which just implements the discretizations I was talking about. And also we are striving to integrate this package with the Julia SciML infrastructure, which provides a really huge library of efficient ODE solvers and of linear solvers and more. The, let's say, mastermind behind this library is Chris Korkas, and as I heard, he will participate in the next long program about fusion next year at IPAM. Yeah? So, and yeah, so this is basically some kind of, let's say, package environment which we have, and I just talk about two more problems we are working on, which are based on this also finite volume approach. One thing is coupling with electroosmotic flow. Basically, this means coupling of this Nernst-Planck-Poisson solver, which is based on the Box finite volume method, with the flow solver, which implements Navier-Stokes equations. And one point has been basically invented by Alexander Linke and further developed by Christian Merdon, is the idea of pressure robust finite element discretizations, which basically allow for pointwise on the discrete level for pointwise divergence-free finite element discretizations. Basically, it's a kind of post-processing of the velocities from the finite element method in such a way that we get, let's say, this pointwise divergence-free velocity, which then allows to get the discrete divergence conditions also in the for the if we introduce the velocity term also to the as an additional driving force for issues motion into the finite volume method, and we can prove that basically based on the upwinding approach that we still get stable solutions and which also are due to natural constraints of concentrations. And another nice thing about this pressure robust finite element method is that just in the error estimates, the velocity error becomes independent of the pressure. Yeah? So, yeah, and that coupling at the moment uses this divergence-free projection of the finite element velocity to the finite volume method, and then we use a fixed band iteration between two solvers to solve the coupled system. we are currently re-implement this also in the Julia environment, and there are also some new approaches to work with automatic differentiation, where basically maybe at some point of time we hope to be able to really have a automatic differentiation for the creation of the full Jacobi matrix of this coupled system. Yeah? So in the moment, we both use automatic differentiation separately and the fixed point iteration, but maybe we can get rid of this. Yeah. So then we can calculate electroosmotic flow, for instance, to some straight nanopore, where we get this kind of plug flow, where we have the Coulomb force driving the flow just only acts in the polarization boundary layer. Yeah? And here we can take the concentrations and velocities at the cross section. So the green line basically is the flow velocity. And here, once again, we can just compare, let's say, the classical Nernst-Planck answer, where we assume infinitely small ions. And at the right side, we look at just this improved model with solvation and finite ion sizes. And here we see that we have a larger electroosmotic velocity, basically because we get larger boundary layers and we have just let's say let's say integrated body force acting on the flux on the velocity field is just stronger due to a wider double layer, and it corresponds to an increase also of the zeta potential with this relation number. Yeah. So another option we are investigating based on the fact that we implemented things in Julia is the possibility of some integration of symbolic tools into the for the creation, for instance, of reaction rate expressions. There are two packages in Julia. One is called Modeling Toolkit, which is a modeling framework for symbolic numeric computation, which basically allows to automatically generate functions for model components. And there's a catalyst model. It's a symbolic catalyst.jl. It's a symbolic package for chemical reaction. So we can define then reaction system symbolic way, basically by just writing chemical reaction equations, and this is then just within Julia code, and this is then kind of symbolically analyzed, and from this we can generate reaction rate expressions, which we then can use in ODE solvers, or also we have some experimental code where we can use these reaction functions generated by catalyst.jl can be used in the reaction rate expressions for boundary reactions, or also for bulk reactions in this Voronoi FEM.gl package. Yeah? So, and this possibility gave rise to a cooperation with the Ringe Lab. So Stefan Ringe and his group will be involved in this long program. He has a paper on coupling CatMap. That's a Python package for expressing and solving microkinetic models, which are parameterized by relative energies of intermediate states obtained from ab initio calculations. He coupled this. He wrote a Python code which couples this with COMSOL, and some kind of fixed point iteration between Nernst-Planck-Poisson and COMSOL, and this Python code is used to get the numerical solutions. And together also with Stefan Maas, we are creating CatMap interface.jl, which uses this finite volume ansatz and this Voronoi FEM package in order to just have a combined solution of this full model. So that means CatMap data are read in as Python code, and Python code so Julia has great interoperability with Python, C, and other languages. And so we can basically get the data from the Python code and transform this symbolically to the direction rate expressions. And then we can use the modeling toolkit also to describe the bulk buffer reactions. And then basically we can just establish, let's say, the same calculation results as from this combined this 2020 paper. So here the red values are from this Python COMSOL combination, and the green curve, which uses this finite volume approach, with just Newton method for the Boole-coupled system of rate equations and Nernst-Planck Poisson transport equations. And also that this approach allows to do the calculations in the wider range of applied potentials. Okay, so this was basically an overview on what I wanted to say. So as we already heard yesterday from Manuel Lernsdorfer, and will be also here once again, just in particular responding to non-constant dielectric permeabilities in the next talk by Manuel Lernsdorfer. Generalized Poisson-Nernst-Planck models are able to reflect quite accurately experimental data. At least we have really very well can see this in equilibrium, but we are also trying to do this in different other contexts. Finite volume methods provide some provable thermodynamically consistent discretization approach for coupled nonlinear systems of PDEs. It's very nice to work with the Julia language, in particular when we want to implement these complicated nonlinear models, because we have the chance to leverage symbolic tools and automatic differentiation. We are trying to apply these things in quite a bit of related fields. Bioelectrochemistry and semiconductor modeling, besides of these electrochemical questions, are also part of this. Yeah, and I also, if there's interest, I would be happy to give more thorough introductions into these methods or the code to try out models during the duration of this long program. So, yeah, thank you very much for your attention, and that's what I wanted to say.